Imagine a perfect absorber and emitter of light. We call this idealized object a black body. When heated, it glows with a spectrum of colors that depend on its temperature. Classical physics, which had served us well for centuries, stumbled when trying to explain this black body radiation. The prevalent theory, based on classical mechanics, predicted that the intensity of emitted light would increase infinitely as the wavelength decreased. This contradicted experimental observations, creating a major problem known as the ultraviolet catastrophe. The inability of classical physics to explain the black body spectrum hinted at a fundamental flaw in our understanding of light and matter. Enter Max Planck, a German physicist who would revolutionize physics with a radical idea-energy quantization. In 1900, Max Planck proposed that energy exists in discrete packets called quanta. Imagine a staircase where you can only stand on specific steps. That's how Planck saw energy. He said energy of each quantum is proportional to its frequency. His equation E equals hn revolutionized physics. Classical physics, using the equipartition theorem, predicted that the intensity of radiation emitted by a black body would increase infinitely as the wavelength of the radiation decreased into the ultraviolet region. This prediction, known as the ultraviolet catastrophe, clearly contradicted experimental observations. The black body spectrum showed a peak intensity at a specific wavelength, after which the intensity decreased for shorter wavelengths. Planck's quantum hypothesis provided a resolution to this crisis. By proposing that energy was quantized, Planck showed that the energy of high-frequency or short-wavelength radiation was also quantized and could only be emitted in discrete packets. This meant that at shorter wavelengths, the energy required to emit a photon was higher, and thus the probability of emission decreased, leading to a decrease in intensity. Planck's law accurately predicted the shape of the black body spectrum, matching the experimental observations perfectly. This marked a turning point in physics, ushering in the era of quantum mechanics. Section 4. Planck's Law, a mathematical description. Planck's law provides a mathematical description for the spectral radiance of electromagnetic radiation at all wavelengths from a black body at a given temperature. The formula is B of lambda and T equals 2hc squared over lambda to the fifth, times 1 over e to the power of hc over lambda kt minus 1, where B of lambda and T is the spectral radiance at wavelength lambda and temperature T, h is Planck's constant, c is the speed of light, k is Boltzmann's constant, lambda is the wavelength of the radiation, T is the absolute temperature of the black body. This formula shows that the spectral radiance depends on both the wavelength and the temperature of the black body. As the temperature increases, the peak of the spectral radiance curve shifts to shorter wavelengths. Section 5. Related laws, Stefan Boltzmann and Wien's displacement. Two important laws are closely related to Planck's law, the Stefan-Boltzmann law and Wien's displacement law. The Stefan-Boltzmann law states that the total energy radiated per unit surface area of a black body is directly proportional to the fourth power of its absolute temperature. Mathematically, it is expressed as P equals sigma AT to the fourth, where P is the power radiated, sigma is the Stefan-Boltzmann constant, A is the surface area, and T is the absolute temperature. Wien's displacement law describes the relationship between the temperature of a black body and the wavelength at which it emits the most radiation. It states that the wavelength of maximum emission, lambda max, is inversely proportional to the absolute temperature. T mathematically lambda max times T equals B, where B is Wien's displacement constant. These laws, along with Planck's law, provide a comprehensive understanding of black body radiation and its dependence on temperature and wavelength. Section 6. From the Sun to Light Bulbs. Practical applications of Planck's law. Planck's law has far-reaching implications for our understanding of the universe. By analyzing the solar spectrum, we can determine the sun's temperature using Planck's law. The law helps us understand the colors of stars. Hotter stars emit more blue light. Incandescent light bulbs are another example. The filament emits light according to Planck's law. As the filament heats up, it emits a spectrum of colors. Planck's discovery laid the foundation for quantum mechanics.